Hello, good morning everyone. I hope everyone had a good time so far and enjoyed the barbecue yesterday. And now we've arrived at the last day of the hackathon, and we're gonna have a talk by Edward, who doesn't really need any introduction, but I guess we can say that Haskell wouldn't be in this state without him. Well, let's leave it open for interpretation. And he's going to give a talk about something somewhat related to Haskell.
Yeah, so Jasper, I think, listed my talk as Haskell on the description of what the talk is about, and I apologize for the bait and switch. There may be a few mentions of Haskell today. So what I want to talk about is a little project that I've been off fiddling with for the last, I guess, maybe 2 or 3 months or so. And it is sort of tangentially related to Haskell in the sense that maybe I can use this as the very, very bottom of the back end of a Haskell compiler at some point here. But I figured when I was going to come out here and give a talk that I should talk about the programming language that everybody knows me for, so I'm going to talk about C++. So I've been off playing around with doing what's called working with a technique for compilation called SPMD on SIMD compilation. And I want to talk a little bit about that. Take a look at what it would take to get it so I could do this in Haskell. Right? I want to bring this back home to Haskell. I'm just not quite able to get there right now. See what I've been able to build up out in the horrible doldrums of C++, and how this sort of fits into the work that's gone into the Haskell Research Compiler from Intel and some other things. Okay, so that should give a broad scope of what I'm about today. So what is SPMD compilation? So how many people here are familiar with like the SIMD instructions on their CPU? Like that they exist at least, you know? Okay, so modern CPUs can execute like 8 additions or whatever in parallel at the same time because you have big fat registers that handle 4 or 8 or 16 or heck, if you're in like the graphics core next architecture on an AMD GPU, they're like 64 wide, 64 integers at a time. That's the size of their registers for the bulk of the registers on the CPU. They're getting nuts. And the problem is like, how do we take advantage of these? A lot of ways that we try to optimize for these things in like LLVM or what have you, is that we unroll our loops, right? That's what we've kind of taught ourselves to do in order to try and get SIMD stuff. You unroll the loop maybe 4 or 8 times, and you hope that you can get enough things that look like the same operation that you can commute past everything else, and then rewrite this into a form that tries to take advantage of the SIMD unit. Okay, I believe Jae-wook Shin called this superword level parallelism or optimistic superword level parallelism, and it's sort of become the mainstay of how compilers try to optimize for SIMD. And the real problem with that approach is that you can look at the data and it tends not to scale once your SIMD units get above about 4 units wide. Okay, because you have to unroll a lot, which means you kind of blow the instruction cache and all sorts of other things start to happen when the optimizations don't apply, or even if they do, and things don't commute as well as you hope. So what I want to talk about today is a technique that's actually closer to the way that GPUs do shaders, but applied to generating CPU code. Okay? And so Intel has a project by Matt Farr. He writes a book, Physically Based Render, PBRT. It's the kind of like common reference in graphics these days for how to do like modern computer graphics as a, like since 2007, all of the games kind of adopt the approach from the PBRT book. And Matt Farr, one of the authors of that book, works for Intel on this project called the Intel SPMD compiler. And what the Intel SPMD compiler does is it takes a different approach. Instead of trying to unroll your loops or what have you in order to find parallelism, what we're going to do is we're going to make it so that if I call your function, I'm going to try and call your function with 8 sets of arguments or 4 sets or 16 sets of arguments. Okay? Which is kind of an alien way to do things. We're We're going to turn things around so that the actual like common definition of an int would actually be a SIMD int. And then the exceptional case will be that we're actually working with a normal int. And the goal here is to shuffle things around so that I'm executing a single program, but with multiple destinations for the data, multiple data. And so if I go to read from memory from a vectored pointer, I'm actually going to be gathering. And if I go to write to memory, I'm actually going to be scattering. And once we've made this sort of shift in our thinking, a lot of things become ridiculously scalable compared to what we normally have to do in order to think about parallel code. Normally when we think about parallel code, we're saying, well, I'm writing so that all of my threads have to cooperate. But when I start talking about threads cooperating, I have to deal with all these memory fences, all these different barriers. If we think about the different logical threads that are executing the same piece of code, where we've got like 8 logical copies of the thread of execution running in the different lanes of your SIMD unit, now, after I finish a step, we're all magically in lockstep. There's no barrier for me to coordinate between those 8 logical threads that have taken a step together. Okay, so within the sort of, in the old GPU vocabulary, this would be what, the warp? You don't have to pay anything for synchronization. Okay, and so the goal here is to try and scale up with the product of the number of cores that I have and the width of my SIMD unit, rather than just with the number of cores that I have. Okay, and to sort of drive this actually works, I can pull up some numbers from the Intel SPMD compiler. So Intel has this, like I said, this dedicated compiler that's written by Matt Farr and a couple of other folks. And we can see these numbers. Zoom in a little bit. This is on just like a random crap 4-core iMac. Using the Intel SPMD compiler versus a standard C compiler, you can see just sort of on a single core, it's just sort of a straight up speed up of about 6x across the board, across a large number of examples. Okay, and on 4 cores, you start seeing the 4 times that, almost directly, embarrassingly parallel speed up on these kinds of applications. Now, a lot of these are sort of biased towards things that like a GPU could do well as well. That's a perfectly fair criticism, and we'll talk about ways to try and regather this parallelism once we've lost it. And that's where a lot of my focus has been lately. Okay, so why am I talking about the Intel SPMD compiler? What I've been doing is I've been building in C++ a library that does what the Intel SPMD compiler does, so that I can, like, through template metaprogramming, just do this in C++, and you just drop some auto keywords throughout your code, and code that you wrote that looked pretty much like the straight line code you'd write in C++ anyways, now just becomes automatically SPMDized, so that this becomes what happens. You have to use a couple of funny templates, and I want to talk about that code. But if you look at what the Intel Haskell Research Compiler did, if you look at the guts of their core language actually has a sort of vectorized primitives for everything. So they always have, like, not just a pointer, but like a vector of pointers or a vector of ints as sort of the core primitives. They don't go all the way to what the Intel SPMD compiler does, but they do at least start speaking about a core that is designed around these kind of vectorized primitives. So I really just wanted to drive home, if I can get a roughly 6x speed up on all the code I write, I'm willing to do an awful lot to change the way I'm doing my code generation to get there. Okay? So I guess at this point, this segues to how do we get C++ to compile an EDSL that looks like this? And this is where I lose the entire audience. So I've been off, I try to learn a new language every year or something like that. So this time I went back and relearned C++. And let's see here. RTS Vec. Horrible, horrible, horrible. Let me see if I can zoom. Can people see this, or should I zoom more? Is that good? Let me see if I can, I can drag that off to the side. Boom. All right. So what I have here is, at the heart of this is this symbol, or this single template, which is that I have a vector of, like, T is whatever type I'm working with, and what instruction set architecture and what width I want to work for. So I have a vector of ints for AVX2 instructions, 8 wide. And we're going to see some horrible things that we have to do in order to trick a modern C++ compiler into compiling functional code decently, or imperative-ish code that is sort of pipeline-ish decently. So here, the sort of stock implementation of this template is that, like, if you want a vector of things, it's just, here's an array of that many items. This is not a terribly surprising data type. We have a bunch of machinery for constructing it, all of the horrible C++ isms to say that, no, really, we want this to always inline, use the attribute always inline, because, like, these things need to turn into single assembly instructions by the time they're done, and if they don't inline, then nothing works. Have to tell it when it may or may not actually throw an exception, so that it doesn't build all the exception handling machinery, because if you try to write modern C++ with exceptions turned on, and you don't do this, then your code is just awfully slow. But if you don't do this correctly and you turn off exceptions, then you're not correct with respect to half the data types out there. And this is just a rotten mess. And then I have to turn around and like start fighting C++ with a million attributes in order to define any individual function here, right? So this is the easiest way to define plus, right? I need to tell it that it always has to inline. C++ or in GCC or whatever, you have like an attribute, underscore attribute tag that you can put on different bits of data, right? You can say here, I'm actually saying this is a pure function. That's what RTS pure does here. Constexpr says this is available at compile time so that you can use this instead of doing horrible template metaprogramming. You can just use this thing directly. Here's what, how do I add a pointer difference to one of my smart virtual function pointers, because I have to be able to point into a vector of things. And these may be stored array of structure or structure of array style. And then these things don't throw exceptions, and yes. The attributes involved here get crazy. But the bit that I think is interesting here is that I started with that one simple vector template, and then I template specialize it as I go. So I start saying, well, if I want a vector of Booleans, these vectors will always be short. They're going to be like 32 or less on current architectures, 64 if I could write code in this style for the graphics Cortex architecture. But here we're just saying, if you want a vector of Booleans, I'm just going to represent it as an int. Unless you're trying to target AVX. And then the native architecture, like AVX instructions, I can pack 4 ints wide in a 128-bit wide register. Okay? So I'm going to pack 4 bools into that same space, which is a terrible economy compared to the previous one, except for the fact that there's assembly instructions that can take this and give me back the bit mask, but there's not assembly instructions that can take the bit mask and give me this thing that I can use for masking off parts of other SIMD computations. Ugh. So here what we're doing is we're going to say, use the built-in data type that Intel gives us through the Intel intrinsics binding that says this is a 128-bit wide integer type that I'm going to have hold either ones or negative ones, and then build all the boilerplate iterator nonsense, make these things do ands and ors. And this gives me sort of a vectorized Boolean that is optimized for that particular SIMD architecture. And I can do the same thing for an 8-wide vectorized Boolean for AVX2, or I could do, let's keep going. past loaders, machinery. Or I want to do load 4 int 32s at a time. Or, 8 int 32s. And that, yes, this unfortunately gets rather repetitive. Because these have to be tweaked to use the individual intrinsic places to do. Let me give a good example. Here's pointers. I have to deal with pointers that can either be 64-bit or 32-bit wide, depending on the architecture I'm on. And then these have to use these awful-looking intrinsic calls that turn into 1 or 2 individual assembly instructions by the time they're done. Okay, this is the trickery to try and get GCC, Clang, and MSVC to emit the single assembly instructions that I actually want this thing to say. Okay, and all of these things have to be written as always inline, because if I call a function in order to do this, it blows away all the wins that I can get from using those individual instructions. Crap. But yeah, so to like load from all of these pointers into this vector, I will do a 64-bit gather of 32-bit data, or 64-bit pointer offset, gather of 32-bit data, et cetera. It's just, I'm writing all of this so you don't have to. So the goal here was to encapsulate all of the nastiness to do these various loads and stores for a given vectorized data type of either pointers or ints or floats, or even if you have, let's go to something that's actually a little more like data.vector. Here, if you wanted to say, I have a vector of complex numbers that's actually stored as 2 vectors, a vector of the real parts and a vector of the imaginary parts. Okay, so this does the, instead of doing an array of structures, it does a structure of arrays. But these are to whatever your native SIMD width is. So this is always 8 or 16 or 4 wide. So why am I bothering? Well, if I start doing like the classic array of structures style thing, that like, classic object-oriented programming tells us that you should try to execute your model somehow. If you look at the cache behavior, it's actually pretty much pessimal to access like an array of objects and say, oh, I want to go add, I don't know, their velocities to their positions. Let's say I'm going to do forward Euler because I haven't read a physics textbook or a game programming textbook or something. Anyways, if I go to add all my velocities to my positions, I'm going to be going to touch all the velocity fields and all the position fields, which are going to be some subset of the fields in a much larger object. I'm going to drag in a bunch of other stuff in from the cache line with it, because accessing one part of a cache line costs me the same as accessing the whole cache line. But if I move to these wide operations, then I use a whole SIMD or a whole cache line worth of velocities, and I'm adding a whole cache line full of velocities to a whole cache line full of positions, and there's no waste. Okay? Sort of by working with these fat objects that are 8 objects at a time, we're able to make it so that almost all of the overhead that I'm getting on a modern CPU is because my data is laid out wrong. Right? If you look at what is the ceiling that is available to you from the sufficiently smart compiler using the data layouts you've given it to try and write smarter code, right? Well, if 90% of my overhead is just going to get the memory, and I only have 10% of the performance left for actually doing something smarter with what I get, there's not a lot of wiggle room for that sufficiently smart compiler to optimize any further, right? The wins that we get in GHC come from the fact that GHC is really good at not putting things on the heap and working, locally in registers. Like we do all these worker wrapper transforms to just avoid making all the intermediate garbage and what have you. It's not because we have a particularly good heap layout. But okay, so I'm just kind of trying to drive home why I'm looking for these fat objects that have several copies of a thing. And we can do the same thing for pairs. I have a vector of the first part, vector of the second part, or we can do template metaprogramming bits to say, if I have a vector of tuples, that actually becomes a tuple of vectors, and I have to do all of the horrible template metaprogramming-ish things to do the get that cuts against the grain to pull the parts out. It actually compiles into efficient code. That's the sad part. Oh, the lambdas vanish. Sorry, the question was even with lambdas? Actually, lambdas are really cheap in practice because they like in C++ land, they become some kind of functor which has some local scope of data, and it just inlines into becoming whatever the target code was going to be in the first place. Especially with all these horrible always inline things all over the place, making my code blow up in size. Let me skim too. I think that's the majority of what I have in this core vector type. So once I've built that one awful template, I can build on top of it to start trying to build a DSL for describing the kinds of computations I want to do here. So this is actually going to be the first abstraction I'm going to introduce that actually has overhead to it. And that's because here I have to keep track of like the current execution mask, which lanes am I using out of my SIMD computation. If I go into like an if or something like that, what I want to do is I want to do an if on a vector of Booleans, right? And what that should do is it say, well, what's the current execution mask? Which SIMD lanes are active, and this vector of Booleans with that, okay? And if anybody wants to take the true branch, then we execute the true branch. Okay, then flip the mask and with the original mask. If anybody wants to take the false branch, take the false branch. And any attempt to assign to what I call a varying int or a varying bool or what, here, will only assign to the parts of it where the current execution mask are set true. Okay, and so if you go into an if statement and in that if branch you say x equals y, we should only cobble the parts of x that are actively being written to, okay? So what I do here is I'm working with a thread local vector of Booleans that is my active execution mask, and it starts with everything active. We're in C++ 14, so I can use a template variable here rather than a... and yeah, so everything here doesn't compile on a compiler older than about 2 months old. But it does compile on every major compiler that is younger than that. And here what we're saying is that a varying quantity is just going to piggyback on all of those horrible specializations I was able to write for vectors. We just have a varying data type, and if I go to read or write to it, it will do all the machinery to mask off. And then here's the only unfortunate part. I can't do an if statement. I have to make my own little if underscore thing that takes 2 lambdas for what to do in the true case and the false case. And we actively mask off the execution, horrible side effecting and equals to avoid some copying. And then check to see if any of those things are true, execute the true branch, etc. So to do for each loops, like let's say I want to do a big like for loop over a big, from 1 to 1,000. What I can do now is I can give you a vector, like 8 at a time of the indices in your for each loop. Okay, and that's how the Intel SPM decompiler gets a lot of its speed, is where it finds its parallelism is using a varying quantity as the loop index inside of some lambda that you give me for the for loop. So we can do if statements for each blocks, and this gives us sort of a straight line programming model. But then we can go off and, so I mentioned before, like, if we're working with a array of structures, we tend to have very bad cache performance for accessing individual parts of a object, right? Because we're accessing some subset of the fields and we get lots of wasted stuff being dragged in with a cache line. And since almost all of our overhead is memory access overhead, unless we're doing crypto, then the crap that gets dragged in along with our data in our cache line is our bottleneck. Well, if we go to do something that needs all of the fields of a record, then doing naive structure of arrays is also the bottleneck. Because you're cutting again, if you need all the field of one record out of a vector of 1,000 of them, right? And you need to go get the the position, the velocity, the name of the guy, all these different pieces for the object or whatever it is that you're trying to serialize out, or whatever. I'm trying to serialize one object out of a game scene or something like that. Then I'm cutting against the grain, and I'm also getting bad cache behavior. Okay, I'm getting bad cache behavior kind of at a page level. So in sort of more modern Intel literature, they tend to favor using what I like to call an array of structure of arrays layout. Okay, and this is like, people see structure of arrays as sort of the logical evolution, but like, let's move one step further here. So what I want to do is I want to do structure of arrays, but for the small fixed size. We've already defined how to do that. We pick whatever the native grain size it should be for my instruction set architecture. And then I want to do arrays of those. So if I want to have 1,000 items, I don't want to have an object with a 1,000 element array and then have to do fancy indexing inside of the thing. What I want to do is I want to work 8 objects at a time until I have 1,007 divided by 8 objects. I have to round up to make sure I get an integral number of fat objects to contain whatever I need. So here, I'm implementing that using a horrible C++ technique that people use called expression templates to try and build a form of like structure of arrays style array that can do a form of fusion to fuse away the intermediate arrays. So if I wanted to say, work with, say, a smarter, I keep going back to game examples because they're something that involves objects, where the objects are actually a reasonable concept to talk about, where you do want to execute something close to your domain model. And here what we have is I probably should have not obfuscated this by using the word vector there. So a structure of arrays for, of, I don't know, complex numbers or objects or people or whatever you have. For n of them, for this instruction set architecture, is calculate up the mask that we should use and shift off the appropriate number of places. So I want, here we're doing like 1,007 divided by 8 vectors of 8 wide items. And then indexing into this becomes a mess because you have to do some shifting and what have you. But constructing this from some other expression that we know how to read is loop through, get a vector at a time, put a vector at a time. So this is automatically SIMD'd. There's no attempts to gather, I don't have to rely on magic loop unrolling and whatnot. This is automatically designed in loop size, in perfect SIMD size chunks. And then if we don't use an integral number of these things, we go get the last element. And there, when we go to get things off, we actually include the mask if we have to be smart about masking off unused bits of data to avoid seg faults or something. Okay, but this is funny because here I'm constructing a structure of arrays from not a structure of arrays, but a structure of array expression. And the result of adding to SOA arrays isn't an SOA array, it's an SOA expression. And the idea here is that this vector get should do the vector get from one half of the thing that I'm adding to the vector get of from the other thing I'm adding. This sort of becomes an object that will do the inner loop of this for statement. And so the goal here is when you say, position equals velocity, or position plus equals velocity time, and then you add half of your acceleration or something like that to do velocity Verlet and do all this other stuff. We want that to turn into a single tight loop with no intermediaries. So here we have the structure of array expression type, which it knows how to vector get something for whatever base type we have. And then I use macros to build templates to, the macros go away. They just give me local domain specific languages. So here I'm building the here's how to do like negation or plus, right? So this builds a SOA expression for that particular type of thing, and then negation, or is that going to be the minus operator here, will build a SOA expression that negates whatever it's reading from or something like that. And they can work with move constructors or not and all the horrible modern C++ semantics that you need in order to be fast. Debugging this has been fun. We can do all the machinery to do, binary operations and yeah. So at this point in time, all of the operations that we have that deal with vector types lift to these SOA types. And then I've been off. Mitchell Charity sent me a bunch of code very recently, porting some code from an older SPMD project of mine. So here we can do things like compute 8 logarithms at the same time or something like that using SIMD-ized code. And this is now instructions. This is instruction set architecture neutral, so this will work, for ARM Neon or for my generic architecture or for the individual Intel ones. And it'll do fuse, multiply, add things to evaluate this particular polynomial to get a polynomial approximation of logarithm that's good over a decent range. And we can do sines and cosines and exponentials and whatever. And I've been slowly building up a math library here. Intel has a math library for the Intel SPM Decompiler, so I can kind of squint and look at what they're doing. I haven't gone through their code in depth yet, though. And my goal here is to get enough math primitives here that this can actually be interesting. You can actually get some serious speed ups out of computing these sort of multiple, like you would hope that the built-in, there's some floating point arithmetic stuff that's supposed to be baked into all these SIMD instruction sets and whatever, but it's not usable as a sort of implementation of most of these numeric types. But I still have to go implement it all by scratch. And the goal here is to build up sort of a good replacement math library. Now, I know in the C++ world, Eigen has a subset of this. You can actually do a lot of this stuff with Eigen today. But one of my particular problem domains is I do a lot of work with Hamiltonian Monte Carlo, big Bayesian models. And I'm interested in being able to drop in this sort of evaluation core at the back end of that. I first encountered this technique when I was playing around with VR stuff last year, and I've got this engine that can do it builds beautiful sunsets at this point, really, and lots of waves. I don't have any art assets, so all I have is procedurally generated things, and so I have to go over the top in order to make anything look good. I have to do caustics and integrate, light through fog and whatever. And so I've been spending all this time working on making better and better versions of this. And I needed to what happened? Oh yeah, so Steam released the Steamvr Audio Sdk, and they used Intel's ray tracer behind the scenes. So Intel has this ray tracer called Embry, and I've spent some time poking around in Embry before. And Embry behind the scenes uses the Intel SPM Decompiler to do most of its ray tracing. And I couldn't use the Steamvr Audio Sdk for my water scene because I wanted Snell's law to deal with the audio, the sort of, how light bends when you look into water? Audio bends when it goes into water as well, but it bends out rather than in because the speed of sound is faster in water, the speed of light is slower. And I couldn't get that effect out of the Steamvr Audio Sdk. For some reason, they didn't necessarily care about when your character's head goes underwater. But if the only thing I have in my scene is water, that's a major component. I have a thing, I can stand chest deep in VR and I can duck my head underwater, and I wanted the sound to sound right. And I didn't have any audio, so all I have is I'm ray tracing until I hit the water surface and then generating some pink noise at that position, and that gives me wave sounds without having to know what waves sound like or go to the beach with a microphone. Anyways, so I wanted to build a better version of that ray tracer inside of my little toy game engine thing, and this drove me off to playing with the Intel SPM Decompiler, which then led to the fact that I couldn't use the Intel SPM decompiler, which is a dialect of C, to talk to my C++ code that was doing all sorts of template metaprogramming, because I had to do on a type-by-type basis. I had to like try and make a custom kernel out in the SPM decompiler that could deal with this particular size of thing for this particular data type. So that's how I wound up here. I admit it's not the most rational of paths. So I started using the Intel SPM decompiler to optimize some code that I have, and it did get me the similar sort of 6x speed up that we see in the Intel SPM documentation. I got some speed ups for dealing with some spherical harmonics code, which you can use for like computing object self shadows for light-based lighting, and I built some code for trying to optimize the generation of the skybox and whatnot that I have, which does all the Rayleigh scattering and stuff, because I only have a sun, so I better try and make the sky blue for some deep fundamental reason rather than paint the sky blue. Anyways, so I was able to get the expected speed ups out of the Intel SPM decompiler, but interfacing with it was a nightmare. By switching over to this approach, what I'm finding is that I can actually get better results than the Intel SPM decompiler, because what the Intel SPM decompiler does is it acts as a thin shim over LLVM. And they just say, hey, LLVM, do the right thing. So they just they do this sort of obvious vectorized compilation of straight line C-style code, and then they just let LLVM pick up from there. But if you take the same kind of code and you hand it to a smarter compiler, like the Intel C program compiler rather than their SPM decompiler, you actually can get like 10 or 15% better performance out of the exact same code. So by re-implementing their compiler as a library rather than as a compiler, I can get about an extra 10% performance boost over what Intel gets. So I wasn't expecting that result. I don't have nearly the full suite of features yet. The code right now is on GitHub under Kmett RTS, and the name there actually sort of leaks where it's starting to what sort of the end goals for all of this. But I want to talk a bit about what are the problems with this model, right? If you start writing shader code, if you write code for GPU, when if I write like shader code for a GPU, it's telling me how am I going to draw a pixel? But I'm actually executing it for like 4 pixels at a time, at least. Or on graphics core next architecture, 64 pixels at a time. And when I'm executing that code path, if any of those pixels takes one of the branches, then I have to execute that whole branch, okay? So the more decoherent the way that I'm drawing these pixels go, the worse and worse my performance gets. So I want to look at ways to try and regain coherence here. So in like C++ these days, like almost everything in the standard library is parameterized over like the choice of mutex that you're using, okay? And off in the world of Boost, there's a little library called Boost Context, which gives a sort of green threading the beginnings of a green threading framework for C++. It's just a fiber switch piece of machinery. So you can create fibers and then cooperatively switch. So you can use it as a building block for a green threading framework. So I can go off in C++ and then use like a work stealing deck kind of arrangement where I have a bunch of workers that have what looks locally like a stack, and where other workers can steal the last thing that would be on the stack, the last task I was going to get around to, and steal jobs back and forth. This is sort of like if I want a lightweight task scheduling thing for a graphics engine or something like that. Again, my go-to example right now is my VR sunset simulator. Then if I work in this way, a thread switch costs me something like 500 nanoseconds right now. A real, honest-to-God thread switch. A fiber switch costs me 5. But I have to know what I'm switching to. And adding the work stealing overhead, we add like another 40 nanoseconds. These are rough numbers, just to kind of get a sense of scale, okay? So switching in this mode is about 45 nanoseconds, which is still an order of magnitude worth of overhead win on the context switch. Okay, so using fibers rather than threads gives me like a factor of 10 for latency. Okay, so go green threading architectures like Haskell. But now what I need to do is I need to have, I can't afford to block like trying to read from a file. If I do like an F read or something like that, that worker is stalled and nobody is using that core. That's the cost of using this sort of approach. So what do you have to do? You have to use some form of like asynchronous IO manager. So now we have to build an IO manager. Fortunately, there's libraries like libevent that you can use that provide us something very comparable to what the GHC, the Haskell runtime system does for, here's a single thread that's actually going to do KQ or epoll or Windows event. All the blocking stuff for getting messaging from the operating system. So that we can say, instead of actually blocking like on a read, what I really want to do is send a message so that my asynchronous IO thread does the block instead, and I start executing a different task. Okay, so we really want a whole lightweight green threading model that I can use in C++. Because I really want to write Haskell, but I happen to be writing C++ at the moment. Temporary insanity, I apologize. And so we can build an asynchronous IO layer there, but now I have to deal with the fact that I have multiple producers and a single consumer for the one queue of stuff that's going to the asynchronous IO thread, and I have a single producer with multiple consumers of stuff coming from the asynchronous IO thread back to the workers, or from my OpenGL thread, because I can only have a single one of those. And now I have to deal with how do I avoid creating garbage in this setting? And I can't afford garbage collection. So I need some way to implement like a hazard pointer scheme or something that can handle like ABA garbage creation, whatever. So I need, like, let's say I have a data structure that I'm going to do compare and swaps to replace things atomically. I have a map, right? Just like, think of it like a Haskell map that I'm going to build, but it's going to be mutable. A mutable map, which I'll just compare and swap new nodes in. If I'm not the only person accessing that map, I have to worry about if I go to delete a node that somebody else was actually accessing it at the moment. In a world of garbage collection, I could compare and swap and then the garbage collector would make that thing go away. In a world without garbage collection, I don't have that power. So there's various schemes like hazard pointers of like holding on to the things that are dangerous that I want to delete, or that until I know that nobody else is touching anything, that let you get rid of those. The scheme that I know of that works the best, even though the literature says it works the worst, is a scheme called epoch-based reclamation. There's actually a wonderful paper from New York Papers We Love. There was a talk given by Sami Al-Bara, who's from the Haskell community, but actually mostly does lock-free concurrency stuff for his day job. And he gave a talk on how epoch-based reclamation wins. He writes a library called Concurrency Kit, which sees a lot of use in the C world for doing lock-free and wait-free data structures and what have you. And the idea of epoch-based reclamation is, what I'm going to do is I'm going to have each worker keep track of like some sort of global epoch counter of like which state of the universe are we in, right? And then it turns out that like you only need 3 current epochs. Like you bump this counter and then you flush out all the things that you tried to destroy like 3 time steps ago, to make sure that you don't delete anything that someone can still be accessing, but you still guarantee progress. Okay, and so you can do this in a way that you pay only proportional to the amount of the amount of things being destroyed, not proportional to the live set. So if I had a big queue, I don't pay for the amount of stuff in the queue, I pay for the amount of stuff churning in and out of the queue. So now, the sub-problem of just trying to get the IO manager so that I can actually keep these workers alive is to go off and build an epoch-based memory reclamation scheme so that my fiber system that I can use to try and regain concurrency so that the SIMD, or the SPMD on SIMD stuff doesn't destroy my concurrency by forking too much. Yeah, that's the next sub-problem. So I have this code, but I haven't integrated it all into this repository. I have this stuff in different projects I'm slowly merging it all into this one. The problem with the work stealing deck is it sort of has a very rigid structure about what happens next. I work with it like a stack, and you're going to steal the last thing I'm going to get to. There was a paper a couple of years ago, actually I guess it was 2013, by Informatikar and a couple other folks, and they, I'm totally forgetting the name of the paper. I will have to send it to the IRC channel or the Slack or something like that afterwards, where they talked about alternatives to work stealing. If you look at sort of work stealing schedule, and you have like the individual tasks that we're going to be performing on the stack have like some kind of expected grain size. You can say, what is the frequency at which tasks will be stolen? And like as your number of cores go up, it gets closer and closer to a Poisson distribution. That like sort of at any given moment in time, you're just as likely to be stealing as any other moment in time. That means that in between those steals attempts, there's sort of an exponential delay. So what you could do is you could turn this whole problem around. You can, instead of stealing, try to give away a job based on some little exponential timer that says, is it time for me to try and force someone to take work from me? Okay, and if you turn this thing around, what happens is each one of my workers now has a little mailbox, and they flip up the flag on the mailbox when they're ready to take work. And all you do is you pick a random other worker and you say, hey, look, is your flag up in here? Here's a task. All is one compare and swap. Okay? And if it fails, you're okay. You tried to steal work on the correct clock. So the nice thing here is that it's not tied to the rigid structure of like a chase-lev work-stealing deck like all of the fork-join parallelism stuff that we have in the Java ecosystem and elsewhere. So what I can do is I can take the this sort of work sharing, this work pushing rather than work stealing machinery, and I can substitute in something other than a deck or how to pick the next task to execute. So an example would be that I could take a small integer priority queue or something like that says, how many copies of the arguments to this function do I have so far? Try and execute a version of this function that has 8 sets of arguments. And take a 7 or a 6 or a 5 or a 4 if there's nothing available. And so what we can do is we can try to say, oh, you really want to call this function. And instead of having what would be like a fork join store style parallelism where you put that into your deck and that becomes a grain that can be stolen. Now what we're doing is we're saying, I really want to call this function with these arguments, and maybe I have 4 sets of arguments for it. Let me queue that up with the other sets of arguments that want to call this function. And when we have 8 of them, now we really want to execute this function. Okay? So the problem up until now has been that we lose parallelism as we go down through if statements and what have you. For each's get me back some parallelism. But if I go into an if statement, my branching costs me. But now if I do a call that is large enough that it's worth paying the sort of fork join parallelism overhead, now what I can do is I can put it into this little priority queue based on how many people are trying to call, or how many attempts do I have to call this function locally? Oh, here's 8 arguments or something like that. Okay, there's a fully saturated attempt to call. Now I'll execute those things with preference over everything else because I don't care about fairness. I care about that every job that has to happen within this frame, it gets done. I care about throughput, not latency, despite the fact that we did all this stuff because the latency concerns of context switches. But this gives us some more machinery. So now we can talk about what is this giving us? We can say we can handle the same kinds of workloads as the Intel SPMD compiler, but you notice that they had a bunch of things that dropped down to like 4x parallelism. And those cases were the cases where the forking, where the branching factor got them down to where they just weren't getting a good utilization out of their resources. So if we can bring that back up, we get a lot of power. And there's a number of places here that are interesting to me. One is, like if you look at the Intel Haskell Research Compiler, the guts of their compiler is to basically execute against the same sort of SPMD sort of execution model. They don't actually use SPMD, they don't actually shut off lanes, but they factorize as much of the internal computations as they can. And they're much smarter about doing things like unrolling because they actually do unrolling than we are in GHC. We don't actually unroll loops. Now I tried actually building this stuff up as a DSL in Haskell. We have some nominal support for SIMD code that Jeffrey Mainland wrote, and Carter Schonwald and a couple of other folks have cared about off and on for the last few years, that the LLVM backend supports. The problem is this, our LLVM calling convention actually doesn't say what to do with 256-bit wide and 512-bit wide vectors. Jeffrey Mainland wrote a patch, and he sent it to the mailing list, and no one really understood it, and it got shot down, and it didn't happen. So this meant that I can't write this code in Haskell today. I was trying to just build a domain-specific language where you could just write here's a varying type family or data family, and then you could just write all the for each and the if combinations. You could build a DSL in Haskell for describing these kind of like shader-like computations you want to do, and then just try and get the 6x speed up in a DSL, like an accelerate kind of thing, but not for the GPU, just for the CPU. And to make that happen, there's a bunch of SIMD primitives that are not exposed by GHC. Like GHC doesn't understand how to do shuffles because a lot of the masks for shuffles had to be compile time constants and stuff like that. We just didn't have a way to talk about that in core. So I sat down and I started chewing on how I could do this, okay? And I can with LLVM, I can write like a custom LLVM file that generates a custom primitive, like using the Haskell calling convention that does a single assembly instruction inside of the primitive. And then I could build a custom link time optimizer pass or LLVM that takes the LLVM object files that we've got and then does inlining following the Haskell calling convention. Okay, because the Haskell calling convention is actually quite straightforward. It's basically all tail calls. And I could inline those definitions that are basically a single assembly instruction into their target. I have to build a custom link time optimizer pass. You have to do a custom build step inside of your Cabal file, but it could be done, right? I could see a world in which this happens. And this would work around the fact that GHC core can't admit those things. The problem is that even with all of that, GHC, because of this calling convention problem, if I go to use a 256-bit wide SIMD register or something like that, it'll actually spill it to the Haskell stack to make the call. So it'll take the two arguments to my plus function, right? Say plus was a primitive that we didn't implement, or like a pop count or something like that. It'll spill it to the Haskell stack, both of them. Then it'll tail call into my primitive. It'll do the addition and it'll tail call up the stack, right? But after spilling the thing out again. So it actually doesn't become inline this thing and do this one operation. It becomes spill, do this thing that I could maybe inline, read, do a single assembly instruction, spill, then execute. There's a couple of tail calls in there. But even if I get the link time optimizer to get in there and shrink that away, it still has all these stack side effects that it's very hard. It would be very hard to convince LLVM are not necessary components, right? So this is the problem that I have right now, is that until I can get the LLVM calling convention fixed for GHC, I can't even build that horrible link time optimizer pass that would let me build the DSL in Haskell so that I could express this as a thought, or or just for doing fast shader-like code in a DSL in Haskell. But thinking about these types in Haskell actually is quite useful for me. If you look at the Intel SPM decompiler, there's a bunch of side cases, like you're not allowed to put a for each statement inside of a for each statement because they're not careful enough to move they don't think about these things in terms of each one of those should have a separate rank 2 style quantifier indicating which scope you're in, and yeah, there's some stuff that should move things into local uniforms and what have you. If you start giving these things rigorous types in Haskell, the proper rank 2 types, you can actually make a fully deterministic version of their DSL. So that's a thing that I cannot express in the C++ side. So for right now, I'm looking at the C++ intermediate thing as a target language, something I want to spit out to from Haskell. And so now we can actually start talking a little bit about Haskell again, aside from the horrible bits of core. So the Intel Haskell Research Compiler compiles down to this language they have called Pillar. And Pillar is a language that they had originally implemented support for directly into the Intel C program compiler, and then they realized that trying to drink from the fire hose of all the changes to the Intel C program compiler was not a viable design strategy. So they built a compiler that compiles down to that thing to C. Okay, I'm trying to do basically the same thing, but targeting down to C++ here, and building my sort of intermediate state, my intermediate language for whatever it is that I'm compiling. For these Bayesian models, or for playing around with graphics problems, or for a little toy Haskell compiler or something. Okay, so my end goal here is I have this little toy compiler that I keep dusting off and then like run into some random issue, and then I go work on that sub issue for 2 years or something like that. So this little this toy quote unquote turbo Haskell compiler that I keep trying to finish. And one of these days I will find the wherewithal to get back to it. And it is sort of the nominal end goal here. So this actually does become a Haskell related talk, is to try and get something where I have a little Haskell compiler that is using this as the runtime system. So hence the RTS name for the repo. And I've been doing a lot of work there to try and build a compiler that can take advantage of this as its execution model. Because the Intel Haskell Research Compiler does show significant performance gains on GHC across a lot of problems, and that's even paying for full operating system threads and what have you. So if I can get away with a factor of 10 or actually more reduction, because now we said before that it was like instead of 500 or 650 nanoseconds, it was 45 nanoseconds, right? But that 45 nanoseconds is now being amortized over 8 logical threads of execution. So it's like 5 or 6 nanoseconds again. My context switch overhead is now 2 orders of magnitude better instead of 1. So if I can enjoy the same kind of performance benefits with 2 orders of magnitude less context switch overhead and cheaper I/O operations and whatnot, there's some promise. But this is definitely on the early end of the research spectrum. So this is sort of the abomination that I've been playing with, and I think I'm happy to take questions. I don't know how much time we have here. All right. So thank you.
So how do you think this would, like this hypothetical turbo Haskell compiler, how would it perform in the cases when you don't actually need those vectorization, when you have not vector heavy code? Would it be comparable to existing one?
Well, so in the case where this is not, where the code doesn't have these sort of obvious parallelism opportunities, right? You still retain the option of trying to do all the classic loop unrolling machinery that like what the Intel Haskell Research Compiler does. So if you do pay the full price of that transform, then you can still try and gain those opportunities. So it wouldn't be that great for that kind of code. I care about code that is going to be sort of large array calculations I can break up into chunks, or large streaming calculations that I can shuffle around the order on in general. So I try to fit my problem to the domain a little bit. I do want to say a couple of things. One is there's a sort of execution model for this that I haven't covered yet. I'm a big those of you who've talked to me about this over the last few years know that I'm a big fan of like tracing JITs, especially for the spineless tackless G machine inside of GHC and what have you. Because the problem with like the way the spineless tackless G machine executes in GHC is that if I go to do a case statement and it's not dynamic pointer tagged, there's like two indirect jumps that are being done. Whereas a tracing JIT actually turns that into, well, is this the same pointer I expect? Okay, great, here, carry on. It becomes a branch, and it becomes very predictable. If we look at what comes out of a tracing JIT, it's a single basic block worth of code that I can then turn sideways like this and execute 8 at a time. I could batch up at the call site. So I have some hope that I can do the same kind of optimization to sort of naive code by just tweaking a JIT. Under the assumption that call site actually is being executed multiple times still. That's sort of been the intermediate road that I've been looking at between writing everything explicitly with these like varying or uniform keywords, and I don't necessarily care whether or not the source language in here is Haskell, right? My first problem domains are like these MCMC problems. My second problem domain is all this graphic stuff. Neither one of those is Haskell specific, right? But then trying to do a Haskell compiler, you wind up with all sorts of weird things like, you have to call a variadic function, a varying function. Well, what do? You mask off, which ones of these are trying to call the same function? Okay, that becomes the same mask, and that becomes the thing that you insert into that set of call sites, if that helps. Right?
Hi. My question is, did you have some example code of using the DSL? Or can I maybe find that in the repo?
I don't have it on this laptop. Unfortunately, I brought 2 laptops with me, but I only brought a power adapter suitable for my Mac. So I don't actually have it on this laptop with me. If you're around tomorrow, I could probably show you some example code that uses the DSL, but I don't have it with me.
Okay.
So for this runtime system, you are using template metaprogramming, which is basically writing code, and then the inline attribute to force the inline of the code that's generated, and even using a macro for generating the template which generates code. Have you considered compiling the Haskell DSL down to C?
C was a thought. One of the reasons why I've been targeting this C++ intermediate layer is that compiling down, like C++ still has a sort of better story for atomics and concurrency and what have you than the story that like the current C standard does. Yes, I could get away with maybe a slightly cheaper compilation step for that last mile. But that is definitely not showing up as my slow point yet. This isn't proving to be a terribly slow DSL to compile to.
I'm asking more not because of the performance, but of the amount of code you had to write in C++ to generate just a few lines of assembly code at the end.
Well, so I could try to directly generate assembly code. So I could build an assembler, and I've done that before. Or I could generate LLVM as a really expensive assembler. Although generating C++ is an even more expensive assembler, so I don't know that that's necessarily an argument. But the FFI story actually becomes much nicer once if I can basically do inline C++ code or whatever DSL that I have that's spitting out this stuff. The FFI story works out much better here. If I need to talk to a third-party library to do components of whatever I want, like if you ever try to talk to a C++ library from Haskell right now, it's an awful experience. Right? And if I do a full native code generator or even like a C code generator, the FFI story is just never there. So I've been kind of targeting this sort of C++ intermediate DSL because A, I can use it for all this other graphic stuff that I'm doing that's literally written in C++, without paying the impedance mismatch of trying to call out to another language. Like if I do that with the Intel SPMD, I would basically be reinventing the problem that I had that caused me to write this little library in the first place, right? Does that make sense? Okay, thank you.
If your application is Hamiltonian Monte Carlo, why wouldn't you just use Accelerate?
Accelerate I've never had a problem for which Accelerate has been the solution. And I realize that is an incredibly glib way to put it, but it's sadly true. Accelerate just doesn't fit my use cases. We can talk about that offline.
I have another question. How did you get more than 4 times speed up with 4 cores?
Keep in mind that we have 8 SIMD units. Or we have an 8-wide SIMD unit. And so the fact that we can get over 32 there is interesting, right? Because we get instruction scheduling benefits from the scattering and gathering. And they can come just a little bit super linear. So yes.
My question is related to the way you could do this in GHC. So as far as I know, in the recent versions of GHC, we have those primitives for up to 8 64-bit
yes.
values. And for primitive operations on them, we have like some really simple ones like plus, multiply, and so on, but we don't have this shuffle functions.
Exactly. We can't do shuffles because shuffles need a mask, and that mask is compiled time constant, and Carter hasn't been able to figure out a way to get anyone to accept that we need those.
But also, I don't know starting from which version of GHC they have this support for putting import prim functions where you could import.
That's exactly. So that was the approach that I was mentioning. Is I could write a foreign import prim, but even if I write a custom foreign import prim right now, if I use a 256-bit wide SIMD register, that foreign import prim will spill to the Haskell stack, the 256-bit wide SIMD register.
But why doesn't it use this calling convention?
Our calling convention needs to be modified. We need 2 lines of code changed in LLVM, change our calling convention, and then we need to change about 4 lines of code in GHC. And that will happen in the next release of GHC in a year.
Great.
Ben Gemaria seemed enthusiastic to make the change. We just need to make sure that we can coordinate with the release of LLVM. The reason it didn't happen 3 years ago was because LLVM was just about to release a thing, and then it just got backburnered indefinitely. So just coordinating GHC releases with LLVM releases was the problem that killed this. And then I guess, I don't know, Jeffrey Mainland finished his PhD or something and stopped caring about the problem. Sorry, Jeff.
So if the whole problem domain here is about doing MCMC, shader computations, and you tried initially to do it inside of Haskell, going through GHC's LLVM code generator, and that kind of didn't work because GHC's LLVM code generator does quirky things and has its own calling convention, why not just target from an embedded domain-specific language inside of Haskell straight to the LLVM bindings where you can do things like very, very granular instruction generation?
Oh yeah, I mean, I could write a compiler in Haskell that spits out LLVM. I could build a modern version of like Haldame's a hierarchical Bayes compiler or something like that, right? As a matter of fact, like
LLVM bindings right now too.
Yeah, my graphics code actually. So the stuff that I do for ray tracing actually generates. I have a domain-specific language for describing how my BRDFs work and how my environment is built up. And then I build a series of compilers for that spit out things from OpenCL to CUDA to just LLVM code directly. That's been the approach that I've taken historically. Okay. Here, what I'm interested in is that most of the code that I'm actually writing is actually on the C++ side, not in the Haskell side right now. And so I could build such a DSL up in Haskell, but then it's a lot of machinery for generating something that still has an FFI problem for talking to anything else. If that makes any sense.
But I mean, if you're going through LLVM, you still get everything in like the C namespace, and you can still point
and C still has a horrible FFI story for talking to C++.
So could this RTS actually target GPUs somehow, like the code you have shown?
I've been looking at it. So the execution model that I use for varying is actually inspired very heavily by the way the graphics core next architecture works internally. Like if you look at the AMD GCN assembly, like the way that those instructions work, they have a series of scalar registers. Then they have a bunch of these 64 wide SIMD registers, and they have a single register that is the current execution mask, right? And every assembly instruction that targets, that writes to one of their registers respects the assembly mask, the register mask and stuff like that. They just have one 64-bit wide mask. So you could, in theory, see that like this could, the same code that is generating out to whatever the C++ EDSL is, could maybe target generating GCN style assembly. I have not been focused on that as a goal, but it fits the execution model, because the execution model is basically inspired by, how is AMD doing this on the GPUs now?
Let's thank the speaker again.
All right, thank you.